So today we're going to talk about clustering. It's our first unsupervised learning algorithm. I'm going to introduce clustering kind of by picture. It's a little bit challenging to do a formal description of clustering, and it's kind of the challenge with unsupervised learning in general. It's not clear exactly what you're trying to do, whereas with supervised learning, it's quite clear, where it's natural to define exactly what you're trying to do in terms of things like loss functions and these sorts of things. But for unsupervised learning, it's a bit of a challenge. So let's jump right in with what's called K-means clustering. So here's some data. Old faithful geyser eruptions. It's a classic data set. It's built into our software package, for instance. And there's two axes. Every point corresponds to one geyser eruption. The x-axis is how long the eruption lasts. The y-axis is how long has it been since the previous eruption. Okay? So it's a scatter plot. And visually, it sure does seem like there's two different groups of things here, right? It's kind of this bunch of things and this bunch of things. Right? And so clustering would roughly be, can we automatically find these two groups, maybe partition the points into two groups automatically. All right. So we'll talk about some ways to do that. This is going to be the K-means algorithm, and we'll kind of present it by example. We'll give a formalization afterwards. But we start with these green points, and we think in terms of cluster centers. So we initialize to two randomly chosen points, the red and the blue x, and we'll think of these as our cluster centers. And we'll assign points to clusters just by distance, Euclidean distance. So if we assign all the points that are closer to this x to one cluster and the ones closer to the other x as the other cluster, that gives us our first clustering. All right? Well, now, this is a clustering. It doesn't look like a good one yet. A clustering is just a partition of the points. Right? So it's a partition into two groups. Well, given this clustering, this partition, we can re-estimate the cluster centers. Right? So let's put each of these x's right in the middle of the cluster. We can take the mean of the points to do that. And we end up with these two new cluster centers. And now we iterate. Now we again assign every point to the center that it's closest to, changing the partition like that, re-estimate the centers, and iterate. Right? Until convergence. Convergence can be that the clustering doesn't change in a round of these updates. So that's K-means. It's as simple as that. Very hard to say much good about K-means theoretically, but we'll give one little statement in a bit. A few caveats about K-means. First, what happens if we run K-means on the geyser data set that we had at the beginning? So we get this clustering. Blue and black are the two clusters. So I'm concerned about this clustering, and maybe you'll see an issue as well. Seems like mostly it's got it, but this point here, it really seems like it should be in the blue cluster. And this point over here, it really seems like it should be in the black cluster. So even though we haven't precisely defined what an ideal clustering is, this doesn't quite seem to look right, at least to my eyes. Do you agree? All right. So what's going on here? Why did this point get assigned to this cluster and this point get assigned to this cluster? So again?
We haven't scaled our data.
Yeah, the issue is the scale of the data. If you look at the y-axis scale, each of these white lines is a jump of 10 in the units of the y-axis, whereas here, this distance is a step of 1. So visually, a small change in the y direction will correspond to a large change numerically in the distance between a point and the centroid. So what's going on here is that this point is closer in the y direction to this point, and the y direction really dominates the distance because the scale is so much larger. Simple as that. So to get the clustering that looks right, we should rescale our data. And then in a normalized scale, the points get assigned basically where you would want them to be visually. All right. So, is this the right thing to do? Well, maybe, maybe not. I mean, maybe the scale where this is plotted is the right relative importance of these two axes. And maybe you want to cluster in this set of scales. There is no right answer. It's just one needs to be aware of the things that are very kind of important in determining what the final clustering is. All right. Here's a failure. It's good to keep in mind some failure cases, right? So Kmeans clustering. Here's a Kmeans clustering on some points. So this is not two diagrams. This is one diagram. So all the points on this slide are part of the same data set. And we've run Kmeans, and we ended up with 3 cluster centers, 1, 2, and 3. All right. And if we kind of run Kmeans in our head, we'll see that this is a converged state of the Kmeans algorithm, right? If we assume all of our clusters are given by the color, and we re-estimate the mean of the cluster, the means will stay in the same spot. Now we assign each point to its closest mean. And indeed, every point is already assigned to its closest mean. So this is a converged state of the Kmeans algorithm. This is something that you can get from Kmeans. This does not seem like a great clustering. Do you agree? I mean, it really feels like this is one cluster, and this should be a cluster, and this should be a cluster. So what went wrong here? Well, it's just a failure of the algorithm. This is a legitimate converged point of Kmeans clustering. What does one do in practice? Kmeans clustering can end you up in a spot like this. It depends a lot on where you initialized your clusters. And so standard practice is to rerun Kmeans clustering multiple times with different random initializations of your starting point. And we'll talk about that a little bit more. So now let's try to formalize this a bit. It'll help to see kind of what are the crucial ingredients going into having a Kmeans clustering algorithm. So the setting, kind of in a more abstract sense, is that we have some space x with a distance metric on it d. So of course, the usual one would be rd with the Euclidean distance on it. But we can be a bit more abstract. We assume we have a data set. N draws a subset of the space x. And the goal is to come up with a partitioning of the data set D into k chunks, k pieces, k clusters, right? C1 through ck. And it'll be helpful to define precisely the centroid of a set of points as this is basically find the point in the space x that minimizes the sum of squares distances between, there should be a mu, not a u, sorry, between each point in the cluster and mu. So find the mu that minimizes this sum. So what would this be in the case of the Euclidean distance? The mean. That's right. That's right. We solved this on homework 2, I think. And so if we didn't have the square there, this is sometimes called Kmedians or Kmedioids. I get confused between the two. They're almost the same. Without the square, what would x be? Well, that's harder. It's high dimensional. All right. So that's a centroid. And this is going to take the place of our cluster centers. This is the generalization of the cluster centers. And so we can write down an objective function, which is, so if someone proposes a set of clusters to you, C1 through Ck. We can evaluate the quality of that by looking at how far each point x is from its corresponding cluster center. So we sum over, for x in the ith cluster, how far is x from the centroid of cluster Ci? And we sum the squares of those distances over all points x. And that's kind of a measure of how good our K clusters are. We can add in the optimization over the cluster centers to get the centroids. And so we could write the objective like this as well. All right. Is that clear? So one application of this is something called vector quantization, where I think the traditional usage is some kind of like a lossy data compression. So you might have points in some Euclidean space, some continuous space, and we would run like a Kmeans clustering on it. Suppose we get K clusters, and then we would represent any element x by the centroid of the cluster, right? So it's not a perfect representation of the point, but it's representing it by some potentially close approximation to it. So if we do that, then in some sense, reconstruction error is exactly, could be represented by this objective function. So how far, what's the average distance, average square distance or total square distance between the actual value of x and its representation by the cluster center? Okay? All right. Cool. So if we were to take this seriously as like a lossy data compression, suppose we have, let's see, do I write it down? Yeah, so the question is, all right, how good can this be as a data compression scheme? How many bits are we going to need to represent a point if we use this vector quantization approach? So if you encode every x by the cluster center it's associated to, what would be a good way to represent these points?
Log number of clusters?
Yeah, log of the number of clusters. Great. So if, for instance, we have 2 to the d, for simplicity, 2 to the d number of clusters, then we can enumerate them and represent that number of the cluster. We basically represent each x by its cluster number. And then how many bits do you need to represent a number from 1 to k? So if it's 2 to the d clusters, then you need d bits. OK, good. A little sidebar on lossy data compression. But there's other reasons for us to be interested in vector quantization. This can be used as a feature. Suppose you want to use a linear model, right? Vector quantization is a nonlinear function of your input that can be quite useful for predicting in a linear model. All right? So perhaps there's clusters of points, and behavior of your function is quite different in each of these clusters. A linear model on the raw input, if this were like R2, can only put planes, can only have linear functions of location. But if we were to do some Kmeans clustering and come up with kind of vector quantization, we could end up with a partition of the space where the partition is based on all points, based on assigning a point to its closest cluster centroid. And then this could give us a feature representation of any point. This would be represented by a 1. This would be represented by a 2. This would be represented by a 3. One hot encoded or something like that. And then your linear model could put different constant values on each of these regions.
So it's like kernel?
Say again?
Kernel.
doesn't feel so much like a kernel to me because it's discrete. You know what I mean? It feels a little bit. If a tree would give you regions, kind of piecewise constant regions, similarly, but those would be kind of axis aligned, right? With vector quantization, we can get this partition into regions that are somewhat arbitrary. So one could try to throw this as a feature into a linear model, for example. Okay. Question?
Could you also do something like inverse distance to each centroid?
Ah, great. So another possible proposed feature is what if you don't just encode which centroid you're closest to? Why not directly make as a feature the distance to each of the cluster centroids? Yeah, that could work too. That could work too. That could be quite interesting. Okay. Great. All right, so the algorithm then is this we know, but we're just recasting it in our slightly more formal setting. So we have our points. We're going to, so there's different ways to choose your initial points. It seems to be recommended to choose your initial centroids to be a subset of your data set. I mean, kind of the reason is if you're in a very high-dimensional space, it's very easy to, if you randomly choose points from this very high-dimensional space, you can end up nowhere near any of your points. Anyway, it seems a little safer to choose points from your data set, and what we'll come to at the end is an actual kind of formal method to choose your initial centroids that has some guarantees, and it does involve choosing from your data set. All right, so we're going to repeat the following until convergence. Convergence just means that your clusters stop changing or your centroids stop changing. So we're going to simply define the cluster to be the set of points that are closest to each centroid in terms of this distance. And then we're going to alternately define the centroid to be the minimizer of this square sum of distances, which would just be the mean for the standard Euclidean distance. All right, so that's it. That's Kmeans' algorithm. And there is a variation of this called Kmeans ++. And this is basically addressing the fact that we could start with a very poor initialization of Kmeans, our randomly chosen centroids, and end up with a poor clustering. What do we mean by poor clustering in this scenario? Like the objective value is higher than it could be. Like with another, we could find other centroids that lower that sum of squares distances to your assigned centroid. So generally, you want to rerun multiple times with different initializations, but we could do better than that. Kmeans ++ is a particular way to initialize it, and I'll just walk through it. So randomly choose your first centroid to be some data point in the sample, and then for each of the remaining k-1 centroids, not dentroids, we're going to compute the distance from each of your points to the closest of the already chosen centroids, and then we are going to kind of randomly sample our next centroid from those points with probability proportional to that distance, the distance to the closest centroid already chosen. Anyway, the most important thing is to know that such a thing exists, and when you're going to do K-means, to keep an eye out for a K-means ++ variant. And it gives you some guarantee on how much worse you expect your objective value to be when you use this initialization compared to the true optimal, the true minimizer of the K-means objective. So just to be clear, just to really be clear on this point, this is the K-means objective function. The K-means algorithm attempts to minimize this, but does not succeed. All right? rerunning it with different random starts will each end you up in some other point, which is locally the best it can do until it gets stuck. And so we do a bunch of random restarts and hope we get a reasonable minimization of this objective. All right. So that's really all I wanted to say about Kmeans. It's often used as a initialization to Gaussian mixture models, algorithms that we're going to talk about next.